Okay, so we've got just to let you know what's going on for the week. We got 3 day one today. It's 1 through 36. It's logarithms. Okay, it's logarithms base 10s and natural base logs. So that's base E. As we go through and step through the notes today, we're going to be doing examples to prep you to do that. We're going to be done with 3 tomorrow. We're going to be graphing stuff for logarithms tomorrow. And then we got 3 day 1 and 2, and the first day of a 3-day deal of 3-5. Remember Martin Luther King weekend, so we're off on Monday. And we have 4 days next week, and we will finish 3-5, day 2 and day 3. We got 3-6, day 1, day 2. We'll be done. Next week, the 22nd. Yeah, 22nd, Monday, 2-hour early release. Day 1 or cleanup of whatever we have left on chapter 3. Tuesday, the 23rd, will be your first day of review, and I have 2 sets of reviews. One that definitely you have to do, the other one's an optional one that I won't collect. And that'll be on Tuesday and Wednesday, okay, as we pace through. And then we have, on finals day, we have a block schedule, and you'll do a version of the final with no calculator and one with a calculator, okay? And the first one's like 12 problems. The second one's like, I want to say 19 problems, something in that area with the calculator. It goes pretty quick. May not be 19, but I apologize for the F word that I used. It is the final test for the semester, but it is the test for chapter 3 specifically. Okay, so during finals week in the block schedule for finals, we will take the chapter 3, no calculator and calculator form. So thank you for the correction. Okay. And then you guys will be done. I will have Friday to get that graded and everything in, and my grades are due that following Monday. Okay, to get on with second semester. So we'll be getting that going then. So keep that in mind. That's the pace. That's what we're going to be doing. And then we'll start second semester, and we will just have a ball. First part of second semester starts with trig functions and going through the unit circle and being able to identify coterminal angles and getting that stuff going. And then second chapter is dealing with graphing all those things. So it's an extremely busy 8 weeks for that first part, that trig part. And then we go back into conics to finish it out. And ellipses, more conics with ellipses, hyperbola, parabola. And then we'll go through in second semester, gosh, I'm missing something, 7 arrays, which is really kind of interesting, working with your calculator and being able to do some stuff with that, but with arrays. But let's get this started. I'm on the wrong page here, so if I can get there, or at least start it up with where we're going. Section 3.3 today. Okay, this is kind of a brief 4-week window about what's going to happen. And this week goes quick, and so does next week. Logarithmic functions and their graphs. At the end of this, I will be able to use inverses of exponential functions, use common logarithms base 10 and base E, graph logarithms base 10, base E, or base 2, you know, whatever the base is, and answer questions about measuring sound in decibels, talking about earthquakes, being able to talk about lumens. All these things are logarithmic based, okay, for our real-world application things. We revisit the horizontal line test from section 1.4. So this horizontal line test, what did we use it for? We determined if a graph had an inverse. Okay, because if it's horizontal line went across, I got a 1-to-1 vertical. It was is showing the fact that we are looking at a actual function. The horizontal line shows whether that function's inverse is an actual function. And if it does pass the vertical line test and horizontal line test, that means the function's 1-to-1. Okay, for the exponential function, f of x equals b to the x power. The inverse is the logarithmic function. Okay. So when we're looking at that, and with the base b denoted log base b of x. So keep in mind, there is a mistake in your notes. We are talking about reflectional skills, not rotational skills. There's no rotation in this. It's a reflection across the y equal x line. So I'm disappointed I didn't catch that, and I was just sitting eating my lunch and reading it, and I was like, well, that's wrong. This would be reflectional methods discussed in section 1.4. Okay, and we talked about being reflected across the line. We switched your x and y values. Okay, and we even will use that idea to graph logarithmic functions. It'll actually graph faster for you. Logs are were first discovered in about 1594. At least the person that we're giving credit to discovery is Napier. He's a Scottish mathematician, John Napier. Originally called them artificial numbers. Okay, there's nothing artificial about them. So they changed that to reckoning numbers, but then became logarithmics or logarithms. Now, if f of x is equal to b to the x, and b is greater than 0, and b is not 1, then the inverse of my f of x is the log with base b, with that happening. So we've got this coming on, and I'll give you time to write that down if you haven't written that down already. Now, this linking statement says that logarithm and exponent, okay, as we look at this, because logarithms are exponents, we can evaluate simple logarithms expressing expressions using understandings of exponents. So we're going to talk about the equivalent statements of, we're going to be given a logarithm, but we're going to be able to rewrite them as an exponential relationship in this first set. And people are like, some people, depending on who you had for Algebra 2, anybody know what the snail shell method, the snail shell deal? Some people are going up and down like this. Other people are looking at me like I just said something that was in a different vernacular or whatever. But here's the deal. If I'm going to rewrite a logarithm, do you guys know what a log really truly is? I mean, it really is asking, when I'm talking about a logarithm base 2, it is asking me, you know, the person looking at this, what exponent do I represent 8 as? You know, what exponent will I need to have? So I have 2 to whatever exponent to represent 8. So right here, we're going to go, well, 2 to the 3rd power is 8, and that's where that comes from. That's 2 to the 3rd power is 8. And really a log to whatever base is asking me to do is return the value of the exponent that I will have that base at to receive that number. And if you kind of keep that in mind as you're going through this, it makes it a little easier. You have a pretty good numeric estimation in your head of what that value should be. So I'm just looking at this and I go, well, 3 to the 1/2 power equals the square root of 3. So 3 to the 1/2 power is equal to the square root of 3. That's all I'm doing. This is me rewriting a log as an exponent. Okay. Are there any questions of what I'm having you do in the next 3? Go ahead, get them done. Go ahead and get them done. That's where that snail shell look comes from. Okay. And if you're really fancy, you can go, ooh, we do the escargot method. Okay. They're snails. That's escargot is snails. See, if you're really fancy. All right. Matter of fact, you guys hear about the snail that wanted S's put on its car, on the doors and on the roof and on the hood and on the trunk. So that way when he drove by or she drove by, they would go, ooh, look at that escargot. Okay, all right, see, bad jokes. But here we go. We're looking at the snail method or escargot method. Are you okay with the setup of these? We're all right. Now, a lot of times when you're doing this, you know, it's just tapping the rust off because you guys have done these before. So we got a couple extra examples. Remember, your base, you got your answer is equal to your argument. Okay, your base, your answer, x, equals to your argument, 27. You're finding identical bases. So when you first do this, the purpose of this is to start recognizing, okay, I am going to write it in an identical base. So 27 expressed as powers of 3. 3 to what power is 27? 3. Okay, so I got 3 to the third power is 27. So now since the bases are the same, I'm really just concerned with solving my exponent. And right now, do you see that my exponent's just got to be 3? So I can set my exponents equal if I get like bases, because I've taken care of the main worry that I have. I could have taken it to the log of base 3 on both sides, and it would have gotten to x equal 3. Okay, but I'm just kind of skipping that step and just going, hey, I'm thinking about the base. Okay, so in this next one, I got log base 4 of 1/64. So I got to be thinking 64. Did you know that's a cubic? Okay, 4 to the third power is 64, but 1/64 is 4 to the negative third power. So when I'm looking at this, I've got 4 to the x, because, you know, I've got 4 to the x of my argument is equal to 1/64. But I recognize that a 64th is 4 to the negative third power. And now I know x is negative 3. So I'm trying to get like bases, so I just set the exponents the same. Because if the bases are the same, the exponents are the thing that I got to solve for here. And in C, doing the same thing, remember, base 2 raised to the x power equals the square root of 32. Now, I've got square root of 32. 32 is 2 to the 5th power. But now I've got this square root thing. And we did this in chapter P. We were talking about the fractional value of square roots. This is the 1/2 power. So my power is the top one. My root is the denominator when I set this up as a fraction. So I'm really raising 2 to the 5th power and taking its square root in that fraction. And now I know x is 5/2. And that's how I can solve for a variable that way when it's in the exponent. Okay, it's one method I can use. But let's go over some basic properties of logarithms. So long as b is positive, okay, it's bigger than 0, but not equal to 1, okay, and x is greater than 0, and any real number y is in there, the log base b of 1, now remember, 1 is my answer. 0 here is my exponent, and b is my base. So really we're going b to the 0 power is equal to 1. That's what that means as we look at that relationship. And I've got log of base b to the b power. Well, b to the first power, right? b to the first power is b. So that's my exponent that I raise b to. My exponent that I raise b to here is y, and they say it's y in this next one. So b to the y equals b to the y. So it makes sense as we work through these powers that log is asking you for what exponent will you put the base of the logarithm, whatever it is, to get your argument inside. Now, when I have a base that's raised to the log b of x, okay, remember log b of x is going to return a number, okay, that is the exponent that you will have if you go b to whatever exponent is equal to x. Well, if that's going to return an exponent, that'll just give me the exponent to make it x. And that's why I'm able to say that, okay, with that relationship. So now, using these properties, I want you to come up with those answers. What, what is the log base 5 of 125? It ends in 5. So find the base of 5 and how 5 times itself how many times? So I've got the log base 5. I got 5 to the 3rd power. Okay, people are like, what's the deal? It's like, dude, it's $1.25. That's 5 quarters. Okay, that's what I'm looking at. So that should return 3 because that's my exponent. Do the same thing in B and C. Now this is the type of stuff you should be able to do calculator free. Remember, this is the same as log of 5 to the 1/2 power. So that's return 1/2 as I go through and work through my problem. And in C, this is the property I'm working on, that B log base B of X is X. So this should just be, as I'm looking at this, I should be coming up with 11. We feeling okay with these for my example 2? Are there any questions? Is the rust kind of shaking off this? You starting to feel like the Tin Man a little bit after we got you some oil, being able to talk? These examples, evaluate the following. Go ahead and get them done. They might be tricky. They might be fun. Is this you? Okay, just checking. It's just, I thought maybe. Okay, so here we go. You ready? If I got a value of 1, that's my, I raised 5 to a power and got a value of 1. It should be 0 as I'm looking at those. Every one of those should be 0. Okay, because my base to the 0 power returns a 1. Now, when I've got this is 12 to the 1st power, so my exponent should be 1, and it's 1 all the way along there. Did you do all right with those? Are there any follow-ups with it using the properties that we have? Now, part of me wanted to put this on tomorrow's notes, but we're going to talk about this, and really what it comes down to, I want you to pay attention to the x values and the inverse of x. Now, we're talking about the inverse of the exponent, okay? And you see, if I have x as 1/8, these two columns, when we did the y equal x reflection, y and x switched positions. So we switched all the values in the data when we did the reflection. So if we go from the exponent here to my logarithm, I can find my numbers as an exponent this way and then switch the x and y and graph them as a logarithm because it's faster that way. All right? Or you could think about it the other way around, and it's possible. I'm not saying it's impossible. It's just more convenient to flip them around like this. But we'll talk about this tomorrow at some more extensively, I guess. Now let's look at common logs. Base 10. Okay. Now, when we're working with common logs base 10, we don't write the base. It's automatically accepted that it's base 10. When I'm working with natural logs base E, I just use ln. I don't use, and I don't include E as a base. In the natural log, ln is just for E. But I can work with different base values for my log. I can go base 2, base 3, base 8, whatever I want to do, okay? But when I don't have a different base, my index has got to be written down. But if I skip it, I'm assuming it's base 10. So the common logarithm function, log of base 10 of x is equal to log of x, is the inverse of the exponential function 10 to the x power. Now, all these properties is what we can apply as we're looking at them for basic properties of common logs. And all I want you to do in example 3 is find our solutions. Go ahead. Remember, the solution should be the power that is used using base 10, 10 is our base, to achieve the argument inside. We're doing okay. And then the bottom two. Should just return me a 6. Are we okay with what's coming up? Any questions? Today's assignment is that type of evaluation. Okay. Now, further examples, as I'm looking through these, give these a try. Now, we just got the basics in there. Now, let's extend those basics to see what our next thing is. They're just not as nice without a calculator. It should be the same one. It's 3x squared plus 2 is that first one. They're the same. So just kind of got really droopy as we went through and had them copy out. I've got some reading glasses. You want to borrow them? Hey, let's see if they work for you. There you go. Okay, I'm using the same properties. Okay, I have not changed anything. I've got log base 7, and it's asking what the exponent is. Well, the exponent's already there. It's just sitting there, but you have to be familiar with the properties just to say, hey, that's what it is. It's 3x squared plus 2. Base of a natural log, well, it's just x. Okay, when I raise a number and it has a logarithm exponent of that same base, it returns the value of the argument, 5x. Okay, does the same thing with the natural logarithm base e. I just return an x. And I got a log base 22 of 22 to the x power. Well, this is just x again. And the last one again is x as well. Maybe. Yeah, there it is. Are there any questions about these? These are great Algebra 2 test questions. Okay? You guys have probably seen them. You worked with them. No problems. Hopefully. Now, using your calculator. Have you noticed that I know I want you to be able to do some stuff without it, but there are some really cool little tricks with it. And the biggest one I can show you, if you're not already familiar, I got to get my calculator up here. I keep forgetting to open it when I start these things. Is the fact that you got this ANS key. Can you locate your ANS key? It's available right above your negative sign, not your subtract sign, the negative sign. It's on the very bottom row of your calculator. You can access it by hitting second negative sign. So on this first one, I just want you to practice the log of 34.5, and it's the common log, okay? And then this is the value you'll get. I want to make sure you can use your calculator with the caret, or you can use it as, however you do it. I call it, the caret to bring it up, and return to get 34.5. Remember, this is the exponent 10's got to be at, to give you an answer of 34.5. And my calculator's finding up, maybe. So you guys practice those. And when checking with your calculator, use the ANS key whenever possible. Otherwise, you may see a rounding error if you just decide to stop writing it out or if you write it incorrectly. Even when using the ANS key, you may experience grapher error because the calculator cannot produce an exact value because for whatever reason the calculator stopped showing the answer that it was doing for you there. Let me just get rid of this. Okay. So just to make sure that we know what we're doing, we got 10 raised up to and I'm looking at my ants, but it's maybe perhaps I should actually do my log. That's there. Log of 34. .5, right parenthesis, and I get this. So just to make sure you recognize this function, I hit my second, I go here, and I get my ants. But before I get that, I got to go 10. I want to raise this to a power. So raise that, excuse me, 10. 10. Raise to my second ants. And it should return, if somebody had done it right. Let's clear this out completely. I'm just going to go back and get my answers for previous things here. So that's the one I got. I'll hit enter, and now I hit my 10, and I raise it up, and I got my second ants here, and that should return my 34.5. Doing both of them that way should work. If you're not comfortable with it, let me know. But I use that a lot in different things for saving calculations. So as we're looking at this next part of our notes, for example 4, this lets us move along. I want you to, we've got these two. I want you to come up with what happens there with C. Okay, can I do that or can't I? No, why not? I mean, did you just enter it wrong in the calculator? No. Okay, as we're looking at this, it's an undefined value. And keep in mind, at each one of these, I should be able to go back and come back with the answer in my calculator. But here is undefined because there's no real number y such that 10 to a power, notice that a power is equal to -3. If I just raise 10 to a power, I cannot change its sign. Okay, I can change how big it is. It can be less than 1, but it's always between 0 and 1. Okay, a power will not change its positive value. Okay, and you'll get an error message. Who returned? Anybody return a complex value, a negative, like point, like I in the calculator or anything? There are some that will adjust to your imaginary values as you're working with your calculator. So we're going to restrict the domain, and this is going to be the positive values that we'll work with in this chapter, the remainder of it, okay, for logs. And we'll do the same thing with natural logarithms. Now, So a lot of me time today as far as the clicking on the boards are concerned. Solving simple log equations. Solve each equation by changing it to exponential form. Okay. So remember, you're doing that idea of the snail method. So I've got 10 is my base, 3 is my exponent, x is my argument. And I can now say, well, it's going to be 1,000. And maybe perhaps some people already knew, but I wanted you to show the relationship you're solving in your head to make it happen. And B, you guys got the same thing. 2 to the 5th power becomes x. So what is 2 to the 5th power? You okay with x is 32? Are there any questions? Using this same method, check out A and B. We'll do A and B first. Remember, it's the same method. 10 to the 2nd power equals z. Okay, so z should be 100. 2 to the 4th power equals z plus 1. 2 to the 4th, 16. Okay, subtracting 1, I find z is 15. Are you okay with the method we're using? Try doing that method to solve for z in problem C. Good. So you guys solving for z in problem C. So it's 1/2 raised to the 5th power. Now, if I evaluate this, I got 32, 1/32. I could choose to solve this. I'm just going to multiply everything by 32 to make it easier. Okay, so that way I can actually make a better fraction at the end too. So I'm going to multiply it by 32 all the way across. This is 1, this is 64z, this is 96. Okay, I'm going to subtract 96. Now I get negative 95. Now, keep in mind, I am solving to find the value of z. Now, if I take that negative 95 64ths, I pop it in to z and multiply that by 2 and add 3. That's the value that I'm looking for. That right now it seems like 1/2 is raised to the 5, is raised to the 5th power. Okay, so it's 1/32. That's the value that will allow me to do that. That's the number I end up with. Questions about how I'm doing it? We're doing okay? Yes, no, maybe. All right, so we got 25, z to the 2nd power, z being what base, and you see that, and it's the 2nd power. I take the square root of both sides, and I'm looking at that being 5, but I got 5 or negative 5. That's concern. Could I actually have negative 5? I mean, we just talked about that. All our answers should be positive. So base of logs cannot be negative values. Or base of logs cannot be negative values, so we won't work it that way. Last one we've got going on this page. I've got a hint there, get the same base. Get the same base to solve. Okay, so 5 raised to the z power equals 5 divided by 125, or 5 1/25. So based on that setup, you simplify and then get the base to the same. It will be a negative exponent that you've got on one side. step 1. Step 2, 5 goes in the 125 25 times. Okay, so when I'm looking at that, I got 5z, okay, 5 to the z power equals 1/25. Well, this is 5 to the negative 2, so I'm looking at z equaling negative 2 when I'm done. Now, some folks saw that right away, and they didn't need to show the work. Other folks, when I have done it right away, they're going, where did that stuff come from? That's why I'm stepping through the way I am. You'll notice how fast I do them on the assignment today, and how I kind of skip that intermediate step. If we ever move on from this, no idea. Yay. Okay. Now, the natural log, folks, it's the same rules, except my base is E, 2.7, dun, 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 dun. And you can find it, just go to your E value, raise it to the first power. But because of their special calculus properties, logarithms with base E are used in many situations. Logarithms with the natural base E are natural logs. And we'll represent it as LN, natural log. So there's a very big difference between the log with other bases and the natural log. So this is, if I just put it in there, I've got that exponent e to the y equal x, doing that snail method that we discussed. But once you know the properties, the basic properties of logarithms of any base and the logarithms of base 10, they extend to the logarithms of base e. It's the same. It's not like 3 separate things you have to know. And I hope that you guys already know that, being Algebra 2 students and getting through there. So now I'm just asking you to express it as exponents in base e. So do the snail method for a, b, and c, please. And come up with your answer. Now, remember, base e raised to some unknown power is equal to e to the 1/2 power. Okay, so that should be 1/2. Here I've got base e, e to the 5th should return me a 5. That's straightforward from the properties that we just looked at. Should return me a 5 if everything worked. If only it would. And then my last one, e raised to the natural log of 4. That's asking me what exponent will e have to be for us to achieve a value of 4. And it gives us that, and then it uses it as the exponent here, so it should just be 4 for my answer. Going down to our last example of today. Evaluate natural logarithms with your calculator. And you can find it. Your second division, I think, has the, I can't help you. I just was looking at, I just want to make sure it's on your division. You also got it right there on your natural log. Just above your natural log, you have a log value there. So be able to evaluate these the same way. You should come out with this same power. Make sure you can do that and work with your calculator. This is an interface of your calculator right now. It says all these answers can come off, should come off your calculator. I'm not expecting you to take 2.78 and everything else to a certain power and come up with an answer without it. Okay, but for the same reason we had with our logs, as we looked at the previous slide. Okay, we have that with our ants, with our calculator shortcut. Okay, for the same reason, you may have those folks that get complex values before will get complex values again. It makes sense, okay, that you got a complex value because it was a negative answer, but we won't be working with those. And you can set your calculator to return those versus giving you the error message, but it's best for you just to know that we're going to be working with the positive value of these. So we're going to restrict the domain of logarithmic functions again to the set of positive real numbers. That's the end of notes today. Okay, we're going to work tomorrow on graphing log functions and answering questions about decimals and lumens. Okay, today's assignment is page 281, numbers 1 through 36. Okay, are there any questions? All right, super, thanks folks.